name is Gary Petco, and I'm your Knox County Schools Math Supervisor. Welcome to KCS Summer at Home Math Video series that go along with your geometry packet that you can find online at our Knox County Schools website. This video goes along with Geometry Section 3 on Trigonometry. Trigonometry, it comes from the Greek word triangle, and then that's the trigon part. Trigon comes from the Greek word triangle, and then metry, the suffix kind of measure. So triangle measure. We're going to talk more about triangle measure. And you've done that up to this point with just triangle saying, I've given you two angles, and can you find the third one if it's a right triangle? Or what if I give you two measures, it's not a right triangle, but you know that the sum is 180. Well, this is going to give you, trigonometry gives you a way to find the measures of angles no matter what, whether it's a right triangle or not, and how can you use that to model contextual situations or real-life situations like what we call angle of elevations and angles of depressions, usually used in surveying or, again, with architecture or with any type of construction. So let's see what we're doing right here. In this section, section 3, it starts off with our good old Pythagorean theorem from the Greek Pythagoras of Samos. We're going to talk about his theorem again and the converse. You touched on a little bit of that at middle school. We're going to revisit it here. Then we're going to talk about special types of right triangles. And then trigonometry and angles of elevation and depression, then laws of sines and cosine. I will tell you from the very start that this is a challenging section because it seems going to be brand new to you, but it still follows the rules of algebra, and it's going to be highly used at your next course if you go into pre-calculus, maybe a little bit of stats, but also into calculus. Okay, trigonometry. The big ideas. What we're going to use are the Pythagorean theorem, or what we call trigonometric ratios. Ratio is not that word is used the exact same way it's used before. It's a comparison of two amounts, and we usually put that one in the numerator, one in the denominator, but these are going to be called trigonometric ratios, or ratios from trigonometry. And then it's called the law of sines and cosines, and they can be used to find the missing side lengths and angle measures of triangles. This is going to give you a series of formulas to help us find the lengths of sides of triangles sides and angles of triangles. As I mentioned earlier, you got the Pythagorean theorem. A squared plus b squared equals c squared. That's the rules, how the sides are related to a right triangle, where the c is always a hypotenuse, the side across from the right angle. And the square of that side is always equal to the sum of the square of the other two. But then trigonometric ratios. If I'm given a right triangle, we've got angles. We can find the measure of the other two angles. We know their sum is 90. Keep that in the back of your mind because there's always a way to double check ourselves. But if it's a right triangle, we've got the angle across from the hypotenuse is always a right angle, meaning 90 degrees. These other two have to add up to 90, but what are they exactly? Well, in trigonometry, the measure of a triangle, we have ways to create ratios. We're saying something called the sine of that. Let's talk about angle A. We can find the actual measure of that because we use the ratio of two of the sides of the triangle. And this says if I take the ratio of the opposite side over the hypotenuse, whatever that amount is, if I take the length of the opposite side and divide it by the length of the hypotenuse, then I get an amount. I can then use the sine to find, that will be the sine of the angle. And we also have cosine, we have tangent. And then we have special right triangles. Special are certain ones that fit the criteria. The two special ones are what we call 45, 45, 90. We got 45 and 45 because these two is named by the angles where these two sides are congruent, but that means the angles are congruent. So a 45, 40, 90 right triangle means the sides are 45, 45, 90. And then a 30, 60, 90 triangle. The angles are 30 degrees, 60 degrees, and 90. When I have that, those special triangles, the sides relate in a special way. For example, in a 45-90, which we know that is an isosceles triangle, an isosceles right triangle, the hypotenuse is always the length of one of the other sides times the square root of 2. Every time it works out that way. And for a 30, 60, 90, the hypotenuse is always twice the size of the shortest leg. And then the longest leg is always that short leg times the square root of 3. And then when we start to put it in context, or what we think of as a real-world problem, we're going to work with angles of elevation or depression. The angle of elevation, if I'm on a horizontal line and I look up, that angle which I'm looking up is called elevation. Elevate, go up. Or angle of depression, if I'm on a building and I'm looking down, it's depressed, moving down, angle of depression. Then two rules, laws of sines and cosines. So we'll deal with all four of these concepts as we go through this section. Going again, chapter vocabulary. We've got angle of depression, angle of elevation I just mentioned. We've got law of cosine, sines, Pythagorean triple. These three question prompts will help you get your mind started. The answers to these are in the answer key at the end, but maybe they'll help you get your mind started because we'll use this vocabulary throughout the section. Okay, let's start off with the Pythagorean theorem. Pythagorean theorem and its converse. As you remember, a squared plus b squared equals c squared. In other words, the legs. The legs are those sides that are not the hypotenuse. If I square those and add them together, that equals the square of the hypotenuse. An example of that. If I'm given a right triangle and I know the hypotenuse is 20 because it's a side opposite right angle, so it's the longest side, they're telling me it's 20. And one side is 12. Can I find the third one? I can using this theorem. I'm just going to substitute values into the appropriate place where the variable it represents. C always represents hypotenuse. I'm going to substitute C in for 20 in for C. And A and B, it really doesn't matter which one of these sides you call A and which one B. Because since I'm adding two numbers, I could put A plus B or B plus A and I get the same. That's the commutative property. So there's where you can't go wrong. So I'm just going to put 12 in for B. I could have just easily put it in for A because either one would have worked. And I'm going to simplify this equation. A squared plus B squared is C squared. Now what we always do is, since we put an X instead of an A because they're asking what is X. They just made that side something we don't know, so we just substitute the letter X for A. X squared plus 12 squared equals 20 squared. I'm going to simplify that. So that 20 squared is 400. 12 squared is 144. If I subtract 144 from both sides, I get X squared equals 256. Then I'm going to take the square root, and X is equal to 16. So that must mean that length is 16. That's using the Pythagorean theorem directly. The converse of it is, can I use that if I'm given the sides? Can I take the three sides and put the values into their appropriate places in the formula? And if I get that relationship where a squared plus b squared equals c squared, then I know I have a right triangle. Okay, special right triangles. They still follow the same rule as the Pythagorean theorem, so you can always fall back on that if you need to. But keep in mind, the special 45, 45, 90 triangle, the hypotenuse, every time if you use that Pythagorean theorem, every time the hypotenuse is going to equal the square root of one of the legs. Which one? Well, it doesn't matter because they're both the same if it's a 45, 45, 90 because that's an isosceles. And the relationship between the sides of a 30, 60, 90, the hypotenuse is always twice the shorter leg, and the longer leg is the square root of 3 times the shorter. So once I know the shorter leg, I can find the hypotenuse and the longer. So here's our question. If the triangle is a 30, 60, 90, stop. It's a 30, 60, 90, it means we're following this set of rules right here. If triangle is a 30, 60, 90, and X represents the length of the longer side, then let's find the length of the other sides. That means if that's what I'm trying to find, the longer leg says the longer leg, which I'm trying to find is X. They're giving me a formula. The longer leg is always the square root of 3 times the shorter leg. So square root of 3 times 20. Now notice we put the 20 on the left side of the radical because just like with a variable, we try to lead with a constant, especially when it's a number. I know the square root of 3 is a constant, but it looks kind of goofy because it's not a number we're normally looking for. So we always put the whole number before the radical. So the longer leg is always 20 times the square root of 3. Now using this formula, if I wanted to, since that's 20, could I find the hypotenuse? Yeah. Because it says the hypotenuse is twice the shorter leg. So if that's 20, this is twice that length, so that must be 40. So I can use this formula. For 8 and 9 in this problem set, I'm going to use the 45, 45, 90 relationship formula. 10 and 11, I'm going to go back to this 30, 60, 90 and look at 12. 12 says a square garden. Stop. square garden means if I take that, if it's a square, that means I've got a right angle. And if I remember from previous work with quadrilaterals, if I do a diagonal, that's going to take that square and turn it into 2 45, 45, 90. So I'm going to use that concept to help me with this, answer this problem. Use this 45, 40, 90 to help with that. Okay, the next two sets of problems revolve around angles of elevation and depression, along with the trigonometric ratios. Trigonometric ratios. Example, what is FE? What is this side to the nearest tenth? That's the nearest tenth means whenever you see in the instructions nearest tenth, that's code for you better get a calculator, because you're probably going to have to do some division that's going to be best suited for a that's going to take us into decimals. This kind is going to be a scientific calculator you're graphing that has a sine, cosine, and tangent buttons. So you know the length of the hypotenuse, and you know the length of the hypotenuse is FE, and FE is the side. Let me start this over again. I just got tongue-tied. Trigonometry makes me do that. So we're trying to find FE. Well, we know the length of the hypotenuse, it's 9. We know this angle adjacent is 41. So now I'm going to use one of these three ratios to find FE. Well, let's see what I'm given. I'm given a hypotenuse. So let's see, these three, if I look at these three sets of ratio equations, that has the word hypotenuse in it. This has the word hypotenuse in it. This last one does not. So it means I'm not going to use that formula. I'm going to use one of these two. Which one? Well, let's look at this. If I'm given, I'm looking for FE. Now notice this word leg opposite angle A, leg adjacent angle A. Well, the amount I'm trying to find FE, is it adjacent to angle that 41 degrees is given to me, or is it opposite it? Now don't get confused because this is angle A and I'm looking for angle E. Angle A just means the angle given to us. So they gave me angle 41. Is that side opposite or adjacent? You're right, it's adjacent. So that means I'm going to use this formula right here because I'm given the hypotenuse and I'm given a side adjacent. So I'm going to use this ratio. The cosine of the 41 degrees is equal to the length I'm trying to find, FE, and the hypotenuse, which is 9. So cosine of 41, I'm using my cross product, so 9 times the cosine of 41. Using my calculator to find the cosine of 41, make sure your calculator is in degree mode. Maybe your geometry teacher talked about that. That must mean FE is about 6.8. I'm going to use these concepts. I'm going to use these concepts to help me solve problems 13 through 17. Okay, last but not least, law of sines and cosine. This is formulas no matter, excuse me, no matter what the triangles, whether they're right triangles or not, these rules work. In a triangle ABC, A, B, and C are the lengths of the sides of sides opposite angles A, B, and C. So they're just telling what these variables represent. So the law of sines will tell us that I've got three sets of ratios that always hold true. The sine of an angle over its opposite side is equal to the sine of another angle over its opposite side, which is equal to another angle, the sine of another angle over its opposite side. But I also got a formula for the law of cosines. If I'm trying to find a side A or side B or side C. So I could use one of these three depending on what information is given to us in the problem. So for example, they're asking us what is GH, this side right here. So the key here is to write down what's been given to us. They gave us the measure of two angles and they gave the measure of one side. So would I use the law of sines or one of these three laws of cosine? Well, if they gave me two angles and one side, this law of sines allows me to use two different angles, whereas the law of cosine only gives me one angle. So I'm going to use law of sines, and I'm going to set it up so the sine of 46 over the GH, which is what I'm trying to figure out, is equal to the sine of 80 over its opposite side. There I've got two proportions, two ratios I set equal. I do the cross products. GH, which is some unknown amount, times the sine of 80 equals 14 1/10 times the sine of 46. Simplify that easy equation, I get GH is about equal to 10.3. I'm going to use one of these two to solve 18, 19, and 20. And I will tell you 21, I might have to use both of them. That's a little test for you. So that's our concept on trigonometry. Let's finish off with a nice quote. This one's by Sonia Kovalevsky, female mathematician, Russian mathematician. She says it's impossible to be a mathematician without being a poet in soul, meaning they go hand in hand. If you're a poet, you love the beauty of things and you express that beauty with words. A mathematician does the same thing. They see the beauty out there and they try to express it with numbers. So they're real similar. All right, this is our section on trigonometry, and I look forward to talking with you about our next section on geometry. Thank you so much.